Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. We are pleased to have Professor Moni Naor here this morning. Moni is a professor of computer science in the Weizmann Institute and a very well-known cryptographer and complexity theoretician. And the title of his talk today is Compressibility of NP Instances. Thank you.
Thank you. So this is joint work with my student, actually my former student, Danny Harnik, who is now a postdoc at the Technion. So I'll be talking about compressibility of NP instances and cryptographic applications. So let's start with the famous cartoon from Gary and Johnson about the poor fellow who has he can't find an algorithm to his problem. So over the years, a lot of techniques have been developed for dealing with problems that where no exact algorithm for the worst case is known, and approximation algorithms, sub-exponential time algorithms, parameterized algorithms, and average case complexity are just to name 4 of them. And what I'm going to discuss today is a new approach, actually my favorite approach for dealing with problems, simply postponing them. So postponing them, or perhaps putting it more nicely, saving them for the future. Of course, the problem with such things, as anyone who has been to my office knows, is that it causes a cluttered disk, or if you're saving it in digital form, a cluttered disk. So really the question is, how can we save problems for the future without storing too much information? So the difference between the usual compression problems is that we're interested in solution with respect to where we want the compression to be with respect to the solution rather with respect to the input. So we're looking for an algorithm Z so that the algorithm Z takes the instance X and compresses it, and the compressed version is in the new language L prime, if and only if the original problem was in the language X. And of course, we want the compressed version to be much shorter than the input X. So we're not, given the compressed version Z of X, we're not interested in reconstructing X. We're only interested in reconstructing whether X is in L or not. That's the only thing we're interested in. So why do we want it? Well, of course, the story I was telling you about storing problems succinctly to be resolved in some future setting. Perhaps there will be faster technologies, maybe quantum computers. Maybe there will be new algorithms, perhaps even P equals NP. And in particular, there is lots of time in the future, so we'll be able to solve it. Okay, so these are several reasons why you could be interested in these things. But actually, the motivation for the work I'm about to describe is from cryptography.
So the previous motivation, suppose in future you have an answer, yes. But you don't know what is this yes for.
Right. Right, the instance is forgotten. So how could it be useful? Okay, we're going to see instances where it's going to be useful. Knowing the 42, knowing that the answer is 42 without knowing the question.
Right.
Exactly. Yeah. So think, or if you want just an immediate thing, just think you have today a lot of data, a lot of statistical data, and you're just interested in finding, let's say you take astronomical data. You're not really interested in, you're interested in knowing some particular, looking for some particular pattern in the sky. So you will discover this particular pattern in the sky, but you will have no idea about the remaining things that existed. So that could be useful even in itself. Okay, so as I said, the actual motivation for this work is the implication of compression for cryptography, both positive and negative, both if compressibility is possible and if it's impossible. So what I'm going to do in this talk, we're in the midst of defining exactly what we mean by compression. We'll see an example of a problem that can be compressed, vertex cover. Then we're going to see a major application, which is construction of collision-resistant hashing. We're going to talk a little about a complexity study of compression, what the various hierarchy that we suggest for a compression. And then we're going to talk about some further cryptographic applications, both ways. Actually, we're going to show some hardness result using cryptographic arguments. And, as usual, some further issues. Okay, so in general, given a large problem, coming up with an equivalent small problem, if the problem is NP-complete, we cannot hope to achieve it. So if we have a CNF formula phi of size m, it's hard to come up with an equivalent formula psi that is much smaller, because otherwise we'll be able to run again the compression algorithm on psi and come up with a smaller problem, smaller and smaller, until we'll be able to solve it exhaustively, let's say. So this is, I suppose, an exercise in SIPSA, why you cannot hope to do this thing. But we're really interested here in problems that have relatively short witness. So the witness to the problem is much smaller than the instance itself, like the galaxy or some particular pattern in the sky versus all the astronomical data. So for such problems, we may be able to compress. There is hope. At least this argument would fail because we're coming up with a different problem than the original one, at least with respect to the parameters. So again, we're going to have two parameters: the instance length, which we're going to denote by m, and the witness length, which we will be denoting by n. And we'll think of our problem as having a part of the first part of their input will encode n and m. It would be obvious what m and n are for any given instance. And the interesting case is where n is much smaller than m, but n is not too small. So it's not something taking time 2 to the n is not something that you can hope to do at least in your lifetime or currently.
How much n and m are related, for example?
It could be, n could be perhaps a large polynomial in n, or it could be larger than that. But it's better to think of them just in these terms. So just think of think of the problem, the SAT problem. You have a CNF formula of m clauses on n variables, not 3 CNF but general CNF. So the witness here is just the satisfying assignment, and the instance size is m or m times n. And again, the compressibility is really we want an efficient polynomial time algorithm Z. We want a polynomial in 2 parameters and a language L prime, such that for every x of length m, the compressed version of x, Z of x, is in L prime, if and only if the original x is in L, and the size of Z of x is polynomial in n and in log n. So this tells you, this partly answers the question. It handles all relationships between n and m, essentially.
For example, n is log m, then it's solve the exhaustive search, of course.
Right, then it wouldn't be very interesting. Right. Okay, so this is our notion of compressibility. So we start with a large problem that has a relatively small witness, but not too small, and we want to come up with a problem which is much closer in size to the witness size rather than the instance size. Okay, so as I said, because so Z of x is really dominated by the witness length rather than the instance length, and of course could be shorter, at least potentially, than the instance itself. Why polynomial in n and log m? You can think of, we actually want to have composability of reductions and things like that. That's why we want this requirement. You could replace it with a sub-polynomial function of m. But for the actual applications that we have, any compression of the form m to the 1 minus epsilon suffices. So we're really interested in just coming up with something for the application we have, for the applications that we have in mind. We're really interested in having a compression of the something which is m to the 1 minus epsilon of the original length. And as I said, this definition is interesting only if n is much smaller than m. For instance, for the 3-sat problem, where the maximum size you can have is compared to the witness, for 3-sat, the instance length can be at most n cubed, otherwise 8 times n cubed, otherwise you'll be repeating yourself. So in this case, there is no difference. There is a fixed polynomial difference between n and m, which is not interesting for compression. Okay, so can we get anything? Yeah?
I mean, why isn't it interesting, let's say, to ask whether your 3-sat
into n squared? So yeah, you could do that. But it's not within the framework I outlined here. Because there exists a polynomial, just n cubed. I'm asking, given okay, or perhaps more generally, there isn't much. You cannot. The problem doesn't let you a lot of freedom here. The 3-sat problem doesn't let you a lot of freedom with respect to the relationship between n and m. It cannot be arbitrary. It's must n cubed.
If m is not polynomial in n, that means that you can solve the problem in sub-exponential time. So that it cannot be NP complete. Or, I mean, unless NP. Yeah.
Okay. So, but really, what I want is I want a fixed polynomial that is good for all n's and n's. So the problem is still NP complete. As we'll see, we're going to see an example of vertex cover, where we'll come up with a particular polynomial, n squared. And this would be the size of the compressed instance, no matter what the original instance size was. Okay, so let's take vertex cover, one of the most famous problems in computer science, of course, one of the original NP hard problems. So we're given a graph G, vertex at V, edge set E, and we want to know whether there is a subset of size n. I'm using the terms just to be consistent with my previous ones, so forgive me for not calling the vertex the size of the graph n, but rather the size of the cover we're looking for as n. So the question is there a subset of n vertices that covers every edge in E? And in our case, this number of edges, let's say, is m, and n is the size of the cover, roughly. Some encoding, not up to some encoding. So we're asking this question. The question is very hard, no matter what the relationship, as long as, for any polynomial relationship between m and n. And the question is there a fixed polynomial where you could compress, given a graph with these parameters, given a graph and these parameters, can you compress it to, can you come up with a graph whose size is only polynomial in n? Yeah?
Maybe you said it and I missed it. When you define the compression, did you ever mention how hard would it be to compress? The complexity?
I want it to be a polynomial in m, a polynomial time in m algorithm. A polynomial in m time algorithm. What I didn't mention is whether I'm allowing randomness or not. For simplicity, in this talk, let's assume that they are deterministic. For most of the talk, let's assume that the compression is deterministic, though many of the examples we have are actually probabilistic. But just for simplicity, let's talk about deterministic compression. Okay, so this is the question. I'm given this graph, parameters, instance size m, witness size n. Can I come up with a graph or with another, with a compressed version of the graph whose size is some fixed polynomial in n? And the answer is yes. There is a very simple compression algorithm for vertex cover. First, you remove all the edges that have more than n neighbors, because such a vertex must be in the cover. If a vertex has more than n neighbors, then you cannot either for each edge, one of its endpoints has to be in the cover, since it cannot be since it cannot be the case that all its neighbors are in the cover, it must be in the cover. So you can remove this vertex and essentially put it in the cover. And you do that, and then after you do that, let's say you've removed k vertices. If there are more than n squared edges left, then answer no. There is no vertex cover. So you can simply store the answer no. And otherwise store the remaining graph G prime, whose size is at most n squared, and the number k. In the language L prime, that is the language of the compressed instance, is essentially vertex cover, but with size n prime, which is n minus k, because we already removed k vertices and put them in the vertex cover. So why is this correct? If a cover exists in the original graph, then in G prime, every edge is covered by one of n vertices, n minus k vertices, and every vertex has degree at most n. Therefore, you cannot cover more than n squared edges in G prime. So therefore, G has a vertex cover of size n if and only if G prime has a vertex cover of size at most n minus k. Very simple argument. And the size, of course, is fixed. It's only n squared. The size of the compressed instance is only n squared. It doesn't matter what m was to begin with. M only affected the time to run this algorithm, but apart from that, it's a fixed polynomial n squared. So what have we learned from this? Well, first, I hope that it clarified the various the relationship between the inputs, etc. But really, what have we learned from this? Okay, one more thing is, notice that it's essentially the same witness. The witness for G prime and the witness for G are essentially the same witnesses. This will come back at the end of the talk. We'll talk about reductions that have this property that is called witness retrievable. So essentially, it's easy to, if you have a witness for G, it's easy, you essentially have a witness for G prime. You don't need to know all of G to know the witness for G prime. Yeah.
To be fixed parameter.
Exactly. Yeah. There is another way to derive it from the linear program. So we see that it's connected to various things, various algorithmic issues. So what have we learned from this? So some interesting languages have non-trivial compression, okay, but really you could say, as Yossi pointed out, that it's because the instance of vertex cover has a small core or kernel that contains the hardness of the problem, and this is related to the parameterized complexity of vertex cover. This is one of the algorithms, one of the fixed parameter algorithms for vertex cover. And it's not necessarily true for other NP problems. So given that we can do vertex cover, what does it tell us about other NP problems? It doesn't tell us directly, it doesn't tell us anything. Can we say the same thing about clique, about dominating set, very closely related problems? We don't know. It's not clear that the point is that the reductions, what's the problem? The problem is that the reductions do not preserve the length of the witness. The usual reductions from vertex cover to clique or whatever do not preserve the length of the witness. So if we started with a small witness, we don't necessarily end with a small witness. So the new witness may be polynomial in M and not, unfortunately, not in N. So we'll be interested, when we'll talk about the complexity, we'll be interested in reductions that are polynomial in their witness size. Okay, so what we're going to do now is, so we saw the definition, we saw an example of a non-trivial, at least a non-trivial compression. I mean, pretty simple compression, but of a compression of an interesting problem. Now we're going to see why we're interested in these things, and we're going to see the cryptographic application. This is going to be technically the most involved part of the talk, of constructing collision-resistant hash functions from one-way functions. Okay, so a collision-resistant hash function, or a collection of collision-resistant hash functions, CRH for short, is a family H of hash functions such that it's given a random member of the family, it's hard to find a collision. So what do we mean by a hash function? That's clear. A function that takes a large domain and maps it into a smaller one. So it's length reducing. So we're interested in collection of length reducing functions. It's hard to find a collision that is given H. It's hard to come up with a pair X and X prime that are not equal, but H of X equals H of X prime, even though there are lots of them because we've compressed the length. It's hard to come up with an actual collision. In hard, we mean for all polynomial time algorithms, all polynomial time Turing machines, if it's the uniform version, or for all polynomial size circuits in the non-uniform version. So we are interested in, of course, we also want the family to be efficient in two senses. It's possible to sample efficiently from the family. So there is an efficient algorithm that samples from the family. The algorithm can either be public coins or private coins. It doesn't really matter. And given H, given the description of H and X, it's easy to compute H of X. Okay? So, so such functions are called collision-resistant hash functions, and they have lots and lots of applications. The most natural application is if you want to sign a large document, digitally sign a large document, then you first hash it by applying such a function, come up with a short string, and actually sign the short string. This is the most straightforward application. It has also more theoretical applications, strong commitments, strong bit commitments, which are statistically hiding, low communication protocols in CS proof, starting with Killian 92, Mikhaili 94, and Boaz-Barak's works, and other applications also for showing problems with the random oracle methodology. So they're a major primitive in cryptography. So these are collision-resistant hash functions. And the other thing I mentioned was one-way functions. So one-way functions are even more basic than a collision-resistant hash. There are functions that are easy to compute but hard to invert. That is, f of x given x, computing f of x is computable that's computable in polynomial time. But yet, no polynomial time machine can come up with inverses. Given y, which is f of x for random x, it's hard to come up with the inverse of y. That is it could be the same x or another x such that, another x prime such that f of x prime equals y. So it's easy to compute, hard to invert. And one-way functions are really the most fundamental building blocks in computationally based cryptography. Without them, you really cannot do much. Without one-way functions, you cannot have encryption except one-time pads. Almost any other task will look like one-time pad. For instance, secret sharing, you can do one-time secret sharing. Shamir secret sharing, you can do it one time. But other than that, if you want to be able to repeat things, you cannot hope for doing it without having one-way functions. And it's sufficient for many of them. Given a one-way function, for instance, we know, at least in theoretically, how you can use it to construct a shared key encryption scheme. So what's the relationship between collision-resistant hash functions and one-way functions? One-way is very simple. Essentially, well, I wrote here the existence of CRH implies the existence of one-way hash functions, but this proof is very simple. By definition, a collision-resistant hash function is also a one-way function. If, let's say, you write f of x if you'll simply write f of h and x equals h and h of x, it should also be a one-way function. So that's very easy. So it's clearly it's a function that is hard to invert. a collision-resistant hash function has to be hard to invert. What about the other way? Other way, actually, it's not known. We don't know how to construct collision-resistant hash functions based on one-way functions. In fact, this is a local result due to Simon in '98. There are no black box constructions of collision-resistant hash functions from one-way functions. So that means, so let's say this is a black box construction. A construction that doesn't look into the program of the one-way function is a black box construction. And almost all the constructions that we have are black box. So what Simon showed is that there is no black box construction of CRH from one-way functions. And we don't know any other thing. So what I'm going to show you is essentially how if compression is possible, you can actually do it. Now, so right now, what's the current status of collision-resistant hash functions in practice? Well, there are two prominent candidates, SHA-1 and MD5, and in both of them, they've been used for the last, I don't know, 15 years or so. Both of them have serious weaknesses, MD5 more than SHA-1, but still they have serious weaknesses. There's going to be a following crypto in a couple of weeks. There's going to be a workshop devoted to coming up with alternative candidates. And the interesting question is do the theoretical difficulties we have in constructing one-way collision-resistant hash functions from one-way functions, are they related to the problems that exist in practice in coming up with these creatures? It's hard one cannot say for sure certainly this is the case, because after all, we're interested in very efficient. When we talk about these things, we're talking about very efficient constructions, and a result like this, for instance, just talks, or the construction that we'll see actually, if it works, would not be particularly efficient. So it's hard to say that it's definitely the case that these two phenomena are related, but nevertheless, it's an intriguing possibility.
In sentence. Is it related?
Okay, so let's say we want to show the equivalence in existence of one-way functions in CRH. We don't know how to show it. On the other hand, right now there is no good. Right now there is also no good agreed upon construction of collision-resistant hash functions in practice. And I'm raising the question whether these two phenomena are related. Okay. So what I'm going to show is that there exists a language L in NP such that if there is an errorless compression for L, then there exists all the compressions that we've been discussing are errorless. Then there exists a construction of CRH from any one-way function. The language actually could be SAT, could be click, could be a whole bunch of other languages. So I'm going to show you a language L and show that if it has a compression, then we can construct collision-resistant hash functions from one-way functions.
It would not be a black box.
It would not be a black box construction, exactly.
You also talking about the other direction?
No, not quite. It's not a win-win situation. Actually, there is a result of Dubrov and Nishai that has this flavor of a win-win flavor that you were hinting at, either this or this. So the idea is start with a naive hash function, a hash function that has no cryptographic hardness. And actually we'll be talking about the selection function. So really we'll be simply selecting a bit at random, and this will be the value of the hash. So the hash function g is defined by position I, and gi of x is simply x at point I. This will be our hash function, and we're going to convert it into a collision-resistant hash function. So this is the string x. Its length is m, and the hash function would simply be choose position I and output the ith location. So in this case, of course, the answer is 1. The new hash function, the actual hash function that is collision resistant, is going to be a commitment to GI. I'm going to define exactly what I mean by commitment. So it's going to be a commitment to GI. This is how it's going to be defined. And the output of H would be a compression of a formula that is equivalent to saying that GI of X equals 1. This is going to be the output of the function H. I'm going to show it in more detail in a minute. Okay, so we start with a very simple hash function. You can hardly call it a hash function, but clearly there's at least some chance that two different strings would not collide. Convert it to a new hash function by giving a cryptographic commitment to GI, and the output of H is going to be a compression of some formula related to X and to G. And actually, in intuitively, finding a collision will require guessing GI, and the commitment is supposed to hide it. So what is a commitment? Commitment protocol is a two-phase protocol, a commit phase and a reveal phase. We have a sender and a receiver. The sender wants to commit to a value I to a receiver, and it's exactly as if it wants to give, not exactly the analog, one should be careful about these analogies, but it's the analog of S giving a locked box to the receiver giving a locked box, the sender giving a locked box to the receiver with a value I inside. So the receiver has it, doesn't know what's inside the box. And the sender does it by sending a string S. And the hiding property is that the computational bounded receiver learns nothing about the value I, cannot distinguish between two, whether the value I is one value or the other value. That's the hiding property. So this is what happens in the reveal phase, in the commit phase. In the reveal phase, the sender opens the commitment, which is as if he sends the key to the receiver, and the receiver can open the box, and out comes I. And the binding property is that S can only be opened to the value I. There's at most one value to which the box can be opened. So I'm describing both phases as a single message phase, where in the first phase the sender sends S, second phase the sender sends V, and the receiver checks. The receiver has some reveal verification algorithm. He checks whether the string S and the value I are consistent with the string V. And the important thing is that there is at most one I for which he accepts the value. There is at most one I for which there is a V that he will accept it as a reveal, as a proper reveal string. Okay? So the nice thing about commitments is that they can be based on any one-way function. And so in our case, we'll be thinking that we have a one-way function on n bits that are hard. So n is going to be the size of hardness required to have one-way function, or actually to have commitments. And m is going to be some value which is larger, which will be related to the compression that we can have. Okay, so here is how we want to prove this theorem, that there exists a language L, which will be very related to SAT. And
it can be based on any one-way.
So if there is a one-way function, if one-way functions exist, then such protocols exist. Okay, there is a fixed polynomial where it will be, where all the strings here, the string length here will be some fixed polynomial in the length of the one-way function. So we want to prove this theorem of coming up with this CRH construction from any one-way function. So we have x of length m, and the string s is a commitment to an index I. Remember that the naive hash function was simply choosing a location here at random. And now let's take, for every j between 1 and m, let's consider the formula Cj, s, and x. So it's a formula, it's a function of S, the commitment to I, of X, the string itself, and J, position J. And this formula is satisfiable if and only if S is a commitment to J and Xj equals 1. Okay? We're interested in this formula. The point is, we can generate this formula without knowing the value I. It's given J, S, and X, we can generate this formula. Why? Because there exists, if S is indeed a commitment to I, then there exists some string that will reveal where the receiver will be convinced that this is indeed I, and we'll simply run Cook's theorem on the reveal verification algorithm. Okay, so we can, and all this is fixed in the small size of the commitment that we have, not in M. Think of M as being something larger than the commitments in the lengths that are in the commitment protocol. So we can generate this formula without knowing I. Now, so we have this, we construct such a formula for each J. And now we're going to take the OR of all these, the OR over all J's of Cj, S, and X. Okay? And this is going to, we get some formula CSX, which is the OR of all these formulas. And the property that we have is that CSX is satisfiable if and only if X of I of the real commitments is indeed 1. Okay? Remember, we wanted to come up with a formula that is satisfiable if and only if the value of the naive hash function, which is simply the ith position, is 1. Okay? And so CSX is the OR of M formula, each of size which is some fixed polynomial in N. The witness size is only, the witness size here is only proportional to N and not to M. It's simply you have to give I and the opening and the reveal string for the commitment that it's indeed I. This is the satisfying assignment to this formula. So it has a small satisfying assignment consisting of, it has a small witness, even though it's pretty large. Okay, so now so now how are we going to define the compression? So H is simply described by the commitment S to I, as I said. The value given S, so the value of HS on X, on input X, is you take the formula CSX and apply the compression to it. This is the value of HSX. So it's polynomial time computable because we just argued that CSX was polynomial time computable without knowing I. And then we assume that we have a compression which is polynomial time computable, so you can apply Z on the formula that we get. And now the first thing to notice is that H is indeed shrinking due to the compression. So we have to choose M to be sufficiently large so that it will indeed be shorter than that Z of CSX would be shorter than M. So H is indeed compressing. And now let's suppose that someone comes up with a collision. A collision X, that is a pair X not equal to X prime, but nevertheless, let's ignore the R, H of Sx equals H of S at point X prime. So what we know is that if S is a commitment to I, then at the position I, they have to be equal. X and X prime have to be equal. So a collision between X and X prime means that the real value I, they have to be equal. Otherwise, the value, remember, the formula that we had here was 1 only if X at position I was 1. So if they're different in position I, one of them cannot be 1 at that position. So we know that they have to be equal and to be equal to 1. So therefore, if x and x prime differ in the jth position, we can conclude that S is not a commitment to the value j. So if you can come up with a collision to this function, that means that you have deduced something about the hidden value I. You've deduced that it's not equal to one of the places where x and x prime differ. And this violates the indistinguishability notion of the hiding property of commitments. So an adversary that can effectively find collisions, that finds an x and x prime, can deduce some information given, not about S, but about I given S. And this contradicts the hiding property of the commitment. The hiding property of the commitment, remember, was that a computationally bounded receiver learns nothing about the value I. Now, more accurately, it cannot distinguish whether the value I is a given value or some other values, whereas here, if you can come up with such a collision, it means that he has a non-negligible advantage in doing it. Okay, so we're using the hiding property of the commitment to argue that collisions are hard to find. And we're using the fact that we have a compression to such formulas to argue that it's indeed a shrinking compression. Okay, so you see some puzzled faces, and I would be very happy to have some questions.
It's not black box because you assumed a particular hash function, correct?
Because of this construction, because of CJSX. We used Cook's theorem. So Cook's theorem caused it to be non-black. Cook's theorem on the reveal algorithm caused it to be non-black box. Yeah, exactly. Pardon?
What do you mean exactly by saying it's a black box, like formally?
Okay, there are a couple of definitions of black box, but this is definitely not black box because I'm using the code of the one-way function via the verification of commitment. Okay, there is the verification algorithm of the commitment here. I started. I took this algorithm. I applied to construct these things, to construct these CJSX. I had to apply Cook's theorem on this on the algorithm, on the reveal verification algorithm. And so I had to have the program. I couldn't just assume that it's given to me as a call to a procedure.
What does Cook's theorem say?
It's the reduction from all NP problems to SAT. But I'm saying it's just can use it here to do it. Okay, so it's not black box construction exactly. And actually, we never have to solve. We're not interested in all. We compress the problem, and we're not interested at all in the complexity of solving the compressed problem. We don't care how difficult is. We've never talked what exactly is the language L prime. All we wanted is that L prime preserve the properties of L. So obviously it's in NP because you can come up with the original witness. If it's errorless, at least it's in NP because you can come up with the original, given a value here, you can come up with the original formula where it came from, and then you can, and then that problem was in NP, so L prime is also in NP. But other than that, we're not interested at all in the complexity of L prime, the compressed language. Didn't affect us. Okay, yeah?
Once again, could you comment on what the compression factor should be in order for this hash function to be shrinking?
Okay, so what is the size of, what matters is the size of CSX. So the size of CSX is M, something like M times poly in N. Some fixed poly in N. Okay? So, and we want to go, the nice thing about CRH I didn't mention is that once you get one bit compression, you can reapply it. So getting just, if you were able to compress it in a single bit, you can reapply it and then get any compression that you want. So at least existentially, it's not the most efficient thing to do, but at least existentially it's possible. So what we want is to be able to go from m times poly n into where the poly comes from the verification algorithm and the Cook's theorem applied to it. We want to go from this to m minus 1. If it's possible to go from a formula of this size to some language whose size is shorter than m, then we're done. So we need, here you can see that it's enough if there is a compression by a factor of 1 to the 1 minus epsilon. Because we can think of m as being much larger than n. It's simply to show that that compression is possible. You wouldn't actually get a compression into 160 bits if that's what you're looking for. You will end up the compression in sizes which are much larger, but at least you can go from very large to large, not to 160 bits as perhaps you want. Okay. So let's talk about, so we saw a particular language. I also hinted that you can easily reduce this language to SAT, to CNF. And we want to somehow understand which problems are interesting. So we want to know which problems can be compressed. For the crypto-positive application, we want to know which problems are sufficient. We're interested in compressing, in coming up with the compression, and we want to know on which language should we concentrate in order to get, let's say, this application. And this is very related to other applications that we have. So, for instance, can we use the compressibility of vertex cover? Well, it's quite obvious that given, it's too simple to be useful, this compression. Maybe if I may describe the compression via linear programming, maybe you would be more convinced that it's relevant. But still, there is a good reason actually to think that it's not relevant, the compression of vertex cover. For instance, now you could ask, is click sufficient? If I can compress click, so I'm given a graph of size m, I'm looking for a click of size n, and I want to come up with another problem. Let's say remain in the click world. I want to come up with a graph of sizes, as we saw here, let's say n squared, which either contains a click of size n or doesn't, depending on the original graph. So if I can do that, is that good enough? Can I use this thing for the crypto application? Now, as I mentioned, so one of them is CRH, another is a construction of oblivious transfer. I'm not sure we'll get to today. For the crypto-negative applications, for which problems is it reasonable to assume incompressibility? So what are the negative applications? Meaning applications that need incompressibility assumption. They essentially need a compressibility assumption in order to work, and there are a number of these. So one of them is hybrid encryption in the hybrid bound and storage model, which I may say something. There is the work of on de-randomization by Dubrov and Ishai on de-randomizing algorithms whose distributions they're using this sort of application in order to de-randomize. And actually there they're able to come up with some sort of win-win situation that I mentioned. Either you can de-randomize or you have a CRH, something of that nature.
I just want to make sure I heard you correctly. So for these kinds of applications, there were reductions which show that if you can do a particular cryptographic primitive, then you have a compressor.
No. The other way around. For something here to work in this model, I may get to it. This is the only thing I may get. Oh, this is actually simpler perhaps to describe. He needs, Jimbovsky, this will be in the coming crypto, he has a paper where he wants to to have a forward secure storage to protect against viruses. And he needs the assumption that there are incompressible languages in NP. Yeah, that you cannot compress. That's why I call this a negative application. Perhaps I should switch the two. I'm not sure. If you can compress, then you get various things. If you cannot compress, then you get other things. Now, hybrid I could have put here as well, because then if there is compression, then I have a cryptanalysis of these schemes. So you could view it both, depending whether you want to design schemes or whether you want to attack schemes. So it's a little hard to say whether it's positive or negative. So, but my point here is that we want to understand the problem. For the positive applications, we want to know which problems to concentrate for and try and come up with compression. And for the negative applications, we want to come up with reasonable assumptions that are of incompressibility languages. I mean, for instance, an assumption like vertex cover is incompressible is not particularly reasonable here for the negative ones. And then, of course, instead of decision, you can ask about other types of problems, search, counting, other types of problems, not only to decide, but to have other information. And then there is the issue, how can the compression algorithm look like? If I want to get to it, some properties that compression algorithm has to respect, and we're going to talk about it towards the end of the talk. So I'm going to say a few words about a hierarchy, a hierarchy of NP, a classification of NP with respect to compression. But it's quite clear that at the bottom of this classification, what we want to have are the compressible languages. Okay, so there are, all languages in P, of course, are compressible. We have a bunch of other examples that follow related to parameterized complexity, which are also compressible. This minimum fill-in for chordal graphs is due to, you can adapt, essentially what an algorithm of Kaplan, Shamir, and Tarjan does is exactly act in the way we want it to act, come up with a certain region, a certain subgraph that contains all the hardness. So this is related to vertex cover. We have other examples of sparse languages where we can use hashing and another form of sparseness of subset hash, a subset sum where we can also use hashing. We can also use sampling. We don't have, these are essentially the examples we have of compressible languages. And all of them behave in a certain manner, which I hinted before, which is called witness retrievable. In any case, we call the languages that you can compress VC0. Yeah.
May it be that we have a problem in P-space that will be compressible?
Yeah, you can talk about things outside P-space, but outside NP, but it's a little harder to because we're concentrating here on the witness size. Okay, we're doing everything with respect to the witness size. So I'm not ruling out compressions outside NP, but they don't quite fall into the framework I'm describing here. Okay, so as I said before, classical NP classification does not suffice for compression, and this is also true for approximation, parameterized complexity, so we need new classification. And the key to the classification is the reduction used, and we define W reduction, W from witness reduction, which essentially says that the witness lengths are preserved. So to language L, W reduces to L prime if it's a regular reduction plus the witness size remains the same within a polynomial in the witness size and logarithmic in the instance size. And the pretty obvious claim is that if W reduces to L prime and L prime has a compression algorithm, then L has a compression algorithm. And you can have matching notions of compression complete and compression hard languages for a class C. And now we want to class.
A complete language.
Yeah, we have complete languages to various okay, we have a complete language for the complete language for all of NP is simply circuit. You have a large circuit with relatively with only n inputs. A circuit of size m with n inputs, that is complete for all of NP. If you can compress this, you can compress all problems in NP. Yeah, but we're interested in in actually much simpler problems, or at least what it seems like much simpler problems. And we do it by the notion I mentioned already, VC. It's from verification class, and we are really interested in how difficult it is to verify a witness. Okay, so in the case of a click, the nice thing about verifying a click, you only have to access part of the input. You only have to access the click part of the input, the edges inside the click. You don't have to access anything outside the click. So that's somehow easier than other problems. For instance, to verify a satisfying assignment to a CNF, you can think of the algorithm as being pretty simple, perhaps more complex than accessing a small part, because the verification algorithm is simply the formula itself is a formula of depth 2. And that's how we construct the verification. We define VCK from K is the depth as having a verification depth K. So the verifying algorithm, given a witness and verifying that it's indeed the correct witness, can be done by a circuit of size of depth K. And the VC1 are the languages that have local verification, where you only need to read part of the input, like click, for instance. And VC0 are all compressible languages. And VC is all of NP. One simple claim is that this is indeed a hierarchy where the only non-trivial thing to prove here is that VC1 is contained in VC2. And I'm not going to say much about these things, because I want to point out, well, the reason we talk about depth, it's not clear that depth is the most important issue here, but at least what happens is that there is a trade-off between depth and the number of variables. The standard techniques to reduce depth imply that you have to introduce lots of new variables. And this is exactly what we don't want to do in these W reductions. We want to preserve the witness size. Yeah, CNF satisfiability is VC2 complete.
Okay, so I'm just having, so the verification.
To verify, given a satisfying assignment, there exists a circuit of depth 2 that verifies it. VC1 are the VC1 are those that have what we call local verification. You don't have to access all the input. We're now switching. It's a little ugly, the difference between VC1 and VC2, because we're switching now from circuits to sort of RAM, where you have to look only at, locally at the, you have to look at the sublinear fraction of the input.
Can you state precisely what is verification depth K? Depth of the circuit?
Depth of the circuit. Yeah. After pre-processing. So you get first a pre-processing stage where can you transform the input to whatever you want it to be, and then the output of the pre-processing has to be a depth K circuit that is given a witness and says yes or no.
So this VC0, what does it mean?
These are the compressible ones. VC0 are the compressible languages.
In terms of depth, depth 0.
Well, it's 0. Well, I mean, yes or no. If you can compress it, yeah. Okay, there is one more class, and that's VC OR. It's simply the OR of lots of NP problems. And so think of it, all of them are satisfying assignments of size, CNF formulas of size n.
The fan doesn't matter.
Well, okay. That's a good question, because to get rid of depth, to go from depth 3 to depth 2, it seems as if you have to introduce a lot of variables. Okay? And whereas going from fan-in to non-fan-in doesn't necessarily introduce more variables.
Verification depth. Do you restrict the fan into two? Or
No. Unbounded fan.
Polynomial time fanning, right? Polynomial size.
So the class is actually the OR of lots of small problems. So one of them has to be in satisfiable. And this class is called VCOR, and this is actually the class that we saw before. Remember, we had an OR of lots of small circuits, lots of small formulas. And so actually what happens is VCOR contains VC0 and is containing VC1. Okay, so that and actually it has lots of, this class VCOR has lots of complete problems. Essentially every NP complete problem, if you take the OR version of it, is complete for VCOR. And the interesting thing is that VCOR is containing VC1, and problems like click are compression hard for VCOR. It's almost trivial. Once you start thinking about it, it's almost trivial to show it. So click is, so that means that for the crypto applications, click is sufficient. If you can compress click, then you can do the crypto application that I mentioned.
What is the definition of compression hard?
That you can reduce every problem in VCOR, doubly reduce every problem in VCOR to click.
Or is not complete to VCOR.
Pardon? Click. It's not known. We don't have a natural problem that is complete for VC1. For VC2, we have, the SAT, CNF SAT is.
What is the smallest K where you can place click into?
VC2. Click is in VC1, which is contained in VC2.
All right.
Okay, so this is sort of a table where you can put various things. So for, as I mentioned, click and long path are all hard for VCOR and reside in VC1. Integer dominating set, for instance, is hard for VC2. Dominating set resides, as far as we know, in VC3, but it's hard for VC2. So for instance, if you could compress dominating set again, you could you get the crypto applications that I mentioned. So you see, so the possibility of the hierarchy, of course, if no compression of complete languages, then of any of the complete languages of these things that we saw, then we have a full hierarchy. If there exists some compression, if there exists a compression to SAT, for instance, then the hierarchy collapses beneath this space. And the question, of course, is where is the border between compressible and non-compressible? This is what we're interested in. And especially we're interested in the low levels, in VCOR, VC1, VC2. It's a little less relevant what happens above them, at least for our applications. So the last topic I want to discuss is the type of reduction, witness retrievable. So remember, I mentioned the property of the vertex cover reduction that we saw was that you have an instance X with a witness WX. You reduce it to, using Z, you reduce it to some instance Y, which has witness WY. Now, we say that the compression is witness retrievable if it's possible to obtain WY in polynomial time from Y and WX. That is, you don't know X, you know Y, you know the compressed instance, you know the witness to the original problem, then you can come up with a witness to the new instance. So this, we call such a reduction witness retrievable. And in the observation that I mentioned, that all the natural simply means those that we thought of, are essentially witness retrievable. So if they're not witness retrievable, you can tinker with them and they can become witness retrievable. And so witness retrievable compression has a further application. I don't want to get into it, but if it's possible, then those of you who know, then minicrypt equals cryptomania, which is Russell and Paiazzo's terminology. which is more or less the most fundamental problem in the foundations of cryptography. I would say that it's probably the problem that, whether these two are equal, is the problem that the problem, some extreme in how fundamental it is, and that there is a chance for resolving it, at least in the positive sense. Even though, again, there are black box operation results. This is the original black box operation result in Prats and Rudish one. So what we can show is that what we can show is that if there exists a language L, similar to the one we saw before, that if it has a witness retrievable compression, then we've resolved the problem. Okay, basically minicrypt means things that are implied. I have actually a table here showing exactly what's in minicrypt and what's in cryptomania. Minicrypt is things that are equivalent to one-way functions. Cryptomania, I've defined it here slightly differently than in PAT, so things that are equivalent to oblivious transfer. Oblivious transfer. Okay, I want to, all I want to say about this slide is that if you have witness retrievable compression of some language, then great things happen. Unfortunately, what we can show is that if one-way functions exist, then there is no witness retrievable compression for SAT. So you cannot come up with a general, perhaps for this specific instances that come up from the proof of that theorem, you can do it, but in general you cannot have a witness retrievable compression algorithm for SAT. And the idea is to use an impossibility, a very simple impossibility result from broadcast encryption if you want to broadcast to a subset. But actually, let's skip that. So let's skip the proof. The point is that we show that you cannot hope to have a witness retrievable compression for SAT. And on the other hand, most of our ideas are witness retrievable. For instance, the idea of you come up with a part of the input where all the hardness resides, as we saw for Vertex cover. So all those natural ideas, all of them are witness retrievable. So that means that if you want to come up with a compression algorithm for SAT, and you believe that one-way functions exist, otherwise I guess some of you wouldn't have much to do if one-way functions don't exist. Certainly cryptography would not be very interesting if one-way functions don't exist. But if you believe that one-way functions exist, that means that you cannot hope to get a compression algorithm that is witness retrievable. So that means that, let's skip that. That leads us to this open problem. So this is really the crux of the matter of this talk. So I'm interested in this problem. I'm giving you, there are two formulas, phi1 and phi2, on the same set of variables. And they're regular ones, not necessarily with short witnesses. And I want to come up with a new formula, phi, that is satisfiable if and only if phi1 or phi2 is satisfiable. Yet its length is shorter than the sum of the two lengths. So there is some encoding here. We have to agree on some encoding so that it will make sense. So the question is whether you can do, the question that comes out of this talk is whether you can do, whether this is possible or not. If it's possible, then we'll have compression for or SAT and all the applications that I mentioned. If it's impossible, then there are some other applications that I hinted about. Now, because we know that you cannot hope to get a witness retrievable compression algorithm, a compression algorithm of this sort has to have the property that a witness for phi1 or a witness for phi2 cannot efficiently yield a witness for phi. So given phi and the witness for phi1, you cannot come up with a witness for phi. So that's not a very natural thing to have. That's not a very natural property to have. You have, so, but it tells us, if we believe that such compression is possible, it tells us what form of compression to look for. So,
do you know any examples of
Non-compressible. I'm sorry.
Non-witness retrievable. So there are some silly ones where you compress, so you have a very sparse language and you compress it using hashing. Then it's not clear exactly that you can always get, given the witness to the original one, you simply used hashing and hoped that there were no, regular hashing, and hoped that there were no collisions, which happens with reasonably high probability, but then it's not clear what you can do with the witness to the original instance. So that's not a very inspiring example. Okay, so you mentioned that I'm going to preach, so you're right. That's what I tried to do here. I think that there are simply too many interesting applications of this issue of compressibility to ignore it. As I mentioned, these are the interesting classes, VC0, VC-OR, VC1, VC2. Of course, it's nice to know about what happens above it, but this is where the crypto applications reside. Of course, so the major issue is where is the line between compressible and incompressible. As I mentioned, implications of incompressibility. One problem with, let's assume that let's say that you want to assume that a problem is incompressible because you're going to use it for some crypto application of the type I didn't describe. Then so you assume that it's hard to compress certain formulas. How do you verify that? How can you publish challenges? It's not clear how you can publish challenges that if people solve them, then you know that the problem is not, then the problem is compressible, that your assumption was wrong. If I assume that factoring is hard, then there are the RSA challenges. I publish them, and they more or less tell me something about the line between whether factoring is indeed hard or not. But here in compressibility, it's not clear how you can publish challenges. This formula is incompressible. Someone comes up with a formula and claiming that it's equivalent. How do you know? There isn't an easy verification procedure for that. So the question is, can you come up with such schemes?
Incompressibility is not a property of a particular formula. It's a property of
the language. Right. Yeah. So I come up with a language and a distribution, let's say. So I'm satisfied with hardness on average here. Okay. And okay, so we came up with one particular classification. It's not clear that it is the correct, or if there is a correct classification. What's the connection to other classifications? It doesn't seem to be directly related to approximability, to parameters. We can steal things from parameters complexity and use them here, but you cannot have anything. You cannot say that if a problem is fixed parameter tractable, then it has compression, or the other way around. As I mentioned, the natural complete problem for VC1 is click complete for VC1. This is does, should be does, not does. I mentioned, if you remember the statement of the theorem about CRH, we required the compression be errorless. Everything I talked about was errorless compression. What if there is a reasonably high probability, polynomial in n, 1 over polynomial in n probability of error in the compression, does it still imply collision-resistant hashing? So, I mean, I think this is perhaps a reasonably easy problem to solve. I mean, not that I know how to do it, but at least it seems easier than the other problems here. So that's it. You have the full paper here, and the compressed version is going to appear at Fox. Thank you.
Do you know of any non-trivial NP-hard languages where every instance can be compressed?
Vertex cover, for instance, is that an answer?
But I think not all instances of vertex cover.
No, okay, the instance is defined by two parameters: the size of the graph and the size of the set that you're looking for. And I come up with an instance which is fixed, which is simply n squared, where n is the size of the set I'm looking for. So all instances can be compressed to size at most n squared, where n is the.
No, I mean, yeah, I mean, can be compressed as a fraction of the original.
Oh, that it will be essentially. No, that it will always be smaller than the original one. No, that's not clear. No. No, I mean, in general, you cannot hope to get it. That's impossible in general from the original, from this picture. Yeah.
So you forget the instance completely.
Yeah. I don't care about the instance. Yeah. Yeah.
Another extreme is to retain the instance. Now there is a big gap
Between
between
the two. Yeah.
So maybe natural have a parameter you forget somewhat, but retain some attributes, some information
about the instance.
We have some more things to play with.
I see. Could be, and then do the classification accordingly. That's certainly a possibility.
Maybe relevant in problems where you have two parameters, two inputs. So I guess that you will have in mind what I have in mind. So you have the graph and the property. And you don't mind forgetting the graph, but you want to remember the property. But the property is usually much shorter than the graph.
Okay, I'm not quite sure. But what do you mean by property? Things like a formula on the graph? Some formula on the graph, or some classification.
Then you want to eventually retrieve specifications that are correct.
And the property is much smaller. Okay, so you can remember it explicitly.
Yes, but yes.
Some attributes of the region.
It's probably worth looking into.
Let me also go back to the original definition. You commented later that you don't really care very much about this L prime.
For the specific, in the case of CRH, for the collision-resistant hashing, I didn't care about L prime. I didn't say that in general I don't care.
So in that situation, you don't care about L prime. The definition of compression seems to just say that you have the sufficiently computable Z, which never produces a collision between an X in L and an X outside L.
Exactly.
Just L prime to separate.
Exactly. Exactly. Yeah.
You mentioned at some point that compressibility is not preserved in the polynomial reduction. Could you give an example?
Oh, I want to reduce the length. I'm given a formula of depth 3. I want to come up with an equivalent formula of depth 2. So I have to introduce a variable for each for each level, for each gate in the input level. So I have increased the size of the one of the levels at least. Increases the witness size.